So I want to go over that. I want to make a comment on the upcoming homework and on the lab that you're working on. And then we're going to start talking about more types of devices, including multiplexers and demultiplexers. I want to show and tell up front first. So I was making a truth table last week in class, and I made the comment that I've written like hundreds of these truth tables in my life teaching, and it would be really cool to have a rubber stamp. And guess what? Somebody 3D printed. So a 3D printed rubber stamp for making truth tables. So stamp it up. And stamp that, and there's the left part of the truth table. So I'll let you out yourself to the class if you want.
Oh, yeah.
There you go, Vlad. So yeah, we have a bunch of 3D printers in the collaboratorium. There's a whole makerspace in there with a lot of tools. And anybody who wants to do 3D printing, right, you can talk to the person in there, take a basic safety course, and start messing with it. And so it's monogrammed. It's got my initials on the top. And I never have to fill in those 64 numbers by hand again, which is like awesome. It's like having 3 extra years added to my life. So that's cool. I can write in my book now. All right, so I'll try to use that when we make truth tables in here. Let's look at the homework that you just got back. Let me see if I can get on Canvas. Yay. So we had a truth table. Hey, look. So inputs were A, B, C, D, and the output was F and G. So 0, 0, 1, 1, 0, 1, 0, 1. All zeros and all ones, and G was a bunch of ones. All right. This part's horrible. That part's beautiful. So it was a function of 4 input variables. And what did it ask you to do? So write the full sum of products for F. So this means no simplification, no using just the little m's, right? Basically write down the product term for each place where you have a 1. So for example, in this third row, 0, 0, 1, 0, F should be equal to 1. So you have to find the product term corresponding to 0, 0, 1, 0. And the rule, which everybody knew, was if the input variable is a 0, you write it with a bar on top. If the input variable is a 1, you write it without a bar. So it's A bar, B bar, C, D bar, C, D bar. And that's the product term for here. The product term for that fourth row would be A bar, B bar, C, D, and so on, and you OR those together. Okay, one thing to be careful of, this term right here, if you write it like that, that's different, right? So don't put the bar over both of them. It's got to be a separate bar over each one. All right, so you take that, you've got 1, 2, 3, 4, 5, 6 terms with a 1 in it, and so you get 6 of these product terms ORed together. Each product term has 4 things being ANDed or multiplied, right? And you don't get to simplify it for the normal full sum of products. Okay, write it in compact minterm form. So minterms start from 0. Okay, this is minterm 0, 1, 2, 3 all the way down to minterm 15. Okay, almost everything we do in computer science, Boolean algebra, we always start from 0. Okay, and if you were to take this binary number and translate it into an integer, that would be 0, that would be 1, that would be 2, that would be 3. That's really where the minterm numbers come from. So f could be written as m2 plus m3 plus m5 plus m7 plus m9 plus m14. And we can also write it as just the sum of 2, 3, 5, 7, 9, 14. So those are compact forms. This is the most compact. And for min terms, we use a little m. When we do max terms, we'll do an uppercase M. All right, and then using a k-map to write the simplified sum of products. So most people totally nailed the k-map, which is excellent. And I'm just going to label this F. And I'm going to put these down on the margins. And I'm going to fill in from the table. So 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. So there's the k-map. And we need to cover it. Well, this one's just got to get covered by itself. That one's isolated, so that's got to get covered by itself. So remember, your goal is to cover every one. You're allowed to cover more than once, okay, but you're not required to. And your overall metric is you want the fewest number of the largest possible rectangles. So I've got to cover this one. I could do a 1 by 1, but I may as well pick up an extra one over here. And I've got to cover this one in the upper right, and instead of just picking it up by itself, I'll pick up the one next to it because that's a bigger rectangle. But I really want to stop right there. I don't want to make another rectangle that covers these two ones. Why? Because they're already covered. Right? So there's no need to cover those with an additional rectangle. And if you put another rectangle in, you get another term in your sum of products, but it's actually redundant. So if you take this and you OR those terms together, right, you're going to get something that automatically captures that rectangle. So you should end up with 4 product terms, and everybody did this mapping correctly also. So this box right here is A bar, B, D. This box is A bar, B bar, C. And then these are just full min terms, so A, B bar, C bar, D, and A, B, C, D bar. And you OR those together, there's your expression for F. Alright, so product of sums is a similar process. So we're doing product of sums for output G. And so write the full product of sums. Okay, product of sums, we always look at the zeros. Sum of products, we always look at the ones. So look at the zeros. So this is for product of sums. Look at the zeros, and then write max terms. And then we want to AND those. So here's a 0 down here. We're going to write the expression for max term M4. And it's the complement of the rule we had here. If there's a 0, so max terms, if there's a 0, we write the variable without a bar. If there's a 1, we write with the bar. And we're ORing these together. So the max term is the OR of either the inputs or the inputs with a bar on top. And when we've got all of these terms, we AND them together. So that's one max term. The second max term would be down here at M5. That's A or B bar or C or D bar, and so on. So there's 6 of those terms to do. And you add them together and you get a big long product of sums. Okay, for compact form, it's the same thing. We just write down the max terms where we have a 0. So this is M4, this is M5, M8, M9, M10, and M11. And that's just coming straight out of the truth table, all the terms that are 0. And these are all ANDed together, so it's a product, which we can write as product 4, 5, 8, 9, 10, 11. So that's a compact form. And then the K-map starts off the same, but again, we're going to look at the zeros. We're going to try to cover the zeros, and we're going to write some terms corresponding to each rectangle. So there's our K-map. Let's fill in all the zeros. So 0, 1, 0, 0. That's a 0 right there. A 0 in the box next to it. And then this block of 4 things corresponds to the bottom row, 1, 0, 0, 0. So these are all zeros. So there's your filled in K-map, and now you need to cover it. And this one's really nice to cover because there's a rectangle and there's another rectangle. And now you write some terms. So over here, A is 0, so we just write A without a bar. B is 1, so we write B with a bar. C is 0, so we just write 0. D can be either 0 or 1, so we don't use it. And we sum these together. And this box down here, A is a 1, so that's A bar. B is a 0, so that's B, and C and D don't matter because they change. So this is A bar or B. And so G is the product of those two terms. So there's your simplified product of sums. So any questions on all of that? And as I say, it looked like everybody basically knew how to do this. The only issues were, possibly writing A bar B instead of A B bar, because we're looking at if there's a 0 in the input, we write the variable without a bar. If there's a 1 in the input, we write the variable with a bar. So the opposite of sum of products. Looking at the zeros instead of the ones, opposite of sum of products. And on the K-map, making sure you don't cover things that are already covered, because it just adds more terms. So I think K-maps are pretty solid for everyone. All right, so how's homework 4 coming? Any questions on it? So a procedural question someone brought up. In part E it says draw a circuit that implements these equations, right? And then in part F it says add properly wired switches and LEDs to the inputs and outputs. I don't need you to redraw the entire circuit in F. If you did, that's fine, but if you haven't done this yet, you can go ahead and just add those switches to the answer for E and just call this E and F. I didn't mean to break it into 2 pieces and make you draw things twice. So that's fine. It's a pretty small circuit though, I believe. All right, everyone good with homework 4? And so homework 5 I haven't put together yet, but I may actually post some questions from from elsewhere. So on the homework, there's sample problems. And I may start using these for some of the homework questions for the next homework going forward. So I'll put a link to it. But if you want to eyeball those, these are good problems to be working on anyway. But we don't go over everything that these questions do. So there may be things in here that we haven't covered, especially around K-maps. So like this question, write all essential prime implicants for the zeros, use these implicants to obtain. So we're not talking about prime implicants or essential prime implicants and so on. So if there's something in here and we haven't gone over it, right, that's to be expected. But if I assign you a question and it's got stuff we haven't gone over, definitely let me know. Okay, but I'll pick and choose. All right, how is the lab coming? So the only thing I want to make clear, right, we talked a lot about this on Thursday, so there's a lot more to what you need to do than just what's written here, right? So make sure you have notes from class. I want to make sure you're clear. You have to include switches and LEDs in your diagrams, right, because you're going to actually build this circuit and test it. So the switches are how you're going to input whether there's a car on each lane, and the LEDs are going to show you the lights at each intersection. So so switches and LEDs along with everything else. All right, good. All right, let's talk about some other components. So I want to talk about multiplexers. Multiplexers are one of these things that, like, the whole world of computers are built around multiplexers in some way. They're a really, really powerful component, but very, very simple in their nature. So here's a block diagram of a multiplexer. So it has two inputs on the left, input 0 and input 1. It has an input on the bottom, which is a select, so I just labeled it SEL, but think of it as selecting. And it has an output on the right, just labeled out. And logically, here's what this block is doing. If this select input is equal to 0, then the output is equal to whatever value is at input 0. If the select input's equal to 1, then the output is equal to whatever value is coming in on input 1. So you can think of this as some kind of magic block that has a little movable wire inside. And this wire either connects input 0 to out or input 1 to out. And the position of that wire, either connecting input 0 or input 1, is controlled by this selection input. If select is 0, you've basically got a wire from here over to there. And whatever happens on the input, that goes to the output. If you put 5 volts on your select, so that's a logic 1, now input 0 is ignored, and input 1 is basically connected to the output. And whatever you feed into I1, that comes out. Yeah?
Is it similar to a switch?
It's exactly like a switch. It's a electrically controlled switch, basically. where we can either, take that input or that input to there. But we get to move that connection by just changing the logic level on the select. So if we made a truth table for this, it might look something like this. So select is 0, input 0 is 0, input 1 is 0. What should the output be? Should be a 0. How about this second row? Select 0, input 0, 0, input 1 0 is 1.
0.
Should still be 0. Why?
Because select is still 0.
Select is 0, so it's reading input 0. How about this third row? And fourth row? Okay. Right, so when select is 0, whatever the input is, that's what the output is. When select is 1, what's the output look like? So in this first case, it's 0. Second case, it's going to read input 1, so that's a 1, 0, 1. And we can design a circuit to implement this. And we could make a K-map, or we could just write a full sum of products or a product of sums or whatever we choose. And if we do all of that work, out's going to turn out to be equal to the inverse of select ANDed with in 0, or select ANDed with in 1. So it's not too bad to implement. A couple of AND gates, 2 input OR gauge. We could also draw this truth table in a different way, which might be more meaningful but won't look exactly like a truth table. If select is equal to 0, what's the output equal to? It's whatever I0 is. And if select is 1, the output is whatever I1 is. And this is kind of a weird truth table, because usually truth tables have 0s or 1s in them. But here I've put the name of an input variable in here. And it's kind of pushing a little bit of work off on the person reading the table. It's saying, okay, if your inputs are 1, 0, 0, what's the output? Well, find what value I1 is, plug that in here. That's what the output is. It's a 0, or it's a 1. And we could modify this truth table even more. And we could write the behavior of it like this. And here I'm using a dash on an input to say that input doesn't matter. So if select is 0 and input 0 is 0, whatever the value of input 1 is, the output's going to be 0. And that's just taking these two rows and combining them into one, saying it doesn't matter if input 1 is 0 or 1, the output's still going to be 0. If select is 0 and input is 1, then the output's going to be 1. And this might most closely sort of capture the conceptual idea of what a multiplexer does. Based on select, it chooses the input and sends it to the output. And so we could write this perhaps by combining those, we could write it with a two-line truth table. If select is 0, the output is I0. If select is 1, the output is I1. So that's fairly informal. We'll talk more formally about what we call compressing truth tables, taking something like this and turning it into that or that. We'll talk about this later on. But this is nice because it sort of really captures the concept of what's going on. Right? The output is equal to exactly one of the two inputs, and it depends based on what the select input is. All right, so that's a 2-to-1 multiplexer. It takes two inputs and gives you one output. And multiplexers are often identified as, you know, A-B, A inputs, B outputs, and it's generally one output. So what would a 3-to-1 multiplexer, these are just called muxes sometimes, what would a 3-to-1 mux look like? Well, 3-to-1 doesn't really make sense. We're going to need two select inputs, so I'll call them select 1 and S0. But if you have two select inputs, how many things can you choose with 2 bits? 4, right? So we don't see 3-to-1 muxes, but we do see 4-to-1 muxes. So our inputs 0, 1, 2, and 3, and an output. And so using this super compact form of truth table, there's the behavior of a 4-to-1 mux. Two select lines, and based on the value of those, we choose one of the 4 inputs and send it to the output. But if we weren't compressing the truth table, what would we get? We'd get a truth table with 1, 2, 3, 4, 5, 6 inputs, 64 rows, a single output. And then you try to write a sum of products or a product of sums, and you do a K-map, and it becomes a big, hairy ball of work. But there's a better way to design a 4-to-1 mux. And this is kind of like what we did with the adder. If we just write the truth table for adding two 2-bit numbers, it's huge. Right? But if we think about the concept of what a 2-bit adder does, we can come up with this idea of designing a full adder and then putting 2 of them side by side. Well, a similar idea here. What we really want to do is take one of these 4 inputs and connect it to this output. So let me show you how you can do that. So each of these is a 2-to-1 mux. Select bit 1 goes in here. Select bit 0 goes into both of these select inputs. And what's the idea here? We've got 4 inputs coming in. We have 2 select signals. So let's suppose that our inputs are 0, 0, our select inputs. So S0 is a 0, S1 is a 0. Well, if S0 is a 0, what's the output right here? Not exactly 0. I0, right. That's fine. And what's the output down here? I2. So now we have I0 and I2 going in here, and if this select is also a 0, what's the output? I0. So that's the correct output if S0 and S1 are both 0. What about the second row? S0 is a 1. Well, let's do the third row because we already did S0 is 0. So S0 is a 0, so this is I0, this is I2. But now S1 is a 1, which means this multiplexer is going to select this input, so the output's going to be I2. And so that's giving us the correct output in that case. Is everybody seeing this? So if S0 is a 1, this multiplexer is going to select I1, this multiplexer is going to select I3. And so if it's a 0, 1, so S1 is a 0, that 0 is going to select I1, and so we get the I1 output. And if S1 is a 1, then this multiplexer is going to select this input, which is I3, and we get I3 coming out. So we don't need the 64-row truth table and all that entails. If we have 3 of these 2-to-1 multiplexers, right, which is just this little 2 AND gates and an OR gate, get 3 of those, put them together, you can make a 4-to-1 multiplexer. And we don't have to stop there. So if each of these is a 4-to-1 multiplexer, and you have 4 select bits, you feed 2 of those bits to these 2 inputs in parallel, and that picks 1 of each of these 4 inputs to pass through to the second stage, and you take your other 2 select bits to choose which of those 4 inputs to pass to the output. And this gives you a 16-to-1 out of 5 4-to-1s. And you can keep going. So you can make big multiplexers out of little multiplexers. And that's a thing. All right, what about the flip direction? There's such a thing as a demultiplexer. So multiplexers go from n to 1. A demultiplexer goes from 1 to n. So let's look at a 1 to 4 demux. So it has 1 input, it has 4 outputs. And it has, if there's 4 things, it's got 2 select bits. And again, think of a piece of wire that you can move around. If your inputs are 0, 0, your input's connected to output 0. If your input is 1, 1, your input is connected to output 3, and so on. And so you set up which output you want to drive based on your select bits, and now whatever happens on the input, that gets sent to that output. So that's kind of the flip side of a multiplexer.
What would a truth table look like?
What would a truth table look like? So 3 inputs, S1, S0, and in, and 4 outputs. So if your select bits are both 0, then output 0 should match your input. And we've got to decide what we want the other outputs to do if they're not being driven. So we might just decide all these other outputs are always going to be 0. And it's only output 0 that's affected by the input. So if the input is 0, 1, then output 1 matches the input, and all the other outputs are 0, and so on. So 1, 0, output 2 matches, 1, 1, output 3 matches, and everything else is 0. And the truth tables for this are pretty darn simple, because for each output there's only one combination of inputs that makes it 1. So it's a single product term if we do a sum of products. Output 3 is just the AND of the inputs. Output 0 is S1 bar, S0 bar in, and so on. So why do we care about multiplexers and demultiplexers? Here's one thing we can do. Suppose we have 4 pieces of information over here coming from something. Maybe this is 4 people typing, or 4 sensors collecting information in your greenhouse. So temperature, humidity, and sunlight, and number of raccoons present or something. Something generating information, right? And we want to send this information to some other location. So over here is the computer sitting in your house, and based on the information it's going to do something, right? Well, one option is to just run a wire from, A over to my computer, B over to my computer, C, D, and so on. But if we have a multiplexer on this end, and we have a demultiplexer on this end, so let's say this is a 4-to-1 mux, and this is a 1-to-4 demux. And we've got some select lines. If we set the select line to 0, 0, what happens? Whatever's on input A gets sent to the output of this mux, and that goes to the input of this demux, and if the select is 0, 0 over here, that will get sent to this output up here. And this becomes a copy of A. And if we set the select line to 0, 1, then B will go to the output, and the input here will go to the second output. So that looks like B. And so by changing these select lines, we can cause these outputs to match these inputs. And so this is part of a bigger theme, which is we have a really thin conduit here, and we'd like to send 4 different pieces of information over. We can choose which one we want to send by just controlling these select bits. And then we can demux it over here and get those bits out. And all of this is stuff that happens inside a computer CPU. And when we get to chapter 4, where we start talking about state machines, once we've gotten through a few of the fundamentals of that, I'll show you a picture of the inside of a CPU. And you'll see that it's nothing but a bunch of multiplexers and demultiplexers doing this kind of thing. Because, for example, what do CPUs have to do? Well, they have to do addition, right? Computers are always adding things in their CPU. If you say I equals j plus k, you got to somehow figure out the value of these variables j and k, add them together, right, and then store that in your variable I. But you've got, you know, tons of things that you might want to add, but usually you have one adder inside. All right, because adders are expensive things to build. You need full adders and half adders and carries and all this stuff. So you might have one adder for the entire CPU. And any time that two things need to get added, you need to somehow get those two things to the inputs of the adder. Well, how do you do that? A bunch of multiplexers. So this might be coming from memory, this might be coming from a set of internal registers, this might be coming from some sort of peripheral device or something else, and the output of this might go into the input of an adder. And if I want to add something from memory, I would set my select line to take the memory output, feed that to the adder. If I want to add the value coming from some peripheral device, I would set my select line to take that input and send it to the input of the adder. So you can build steering networks with multiplexers, and steering networks basically let you take data and move them around inside a CPU or anything else. And that's a part of a CPU usually called the data path. How many computer science majors in here? Whoa, I don't have to be gentle then. Because double E's also take this course. Cool, lots of CS. Yeah, so if you take a course in computer architecture, which is usually like, you know, a third or fourth year class, you learn about the design of a CPU, right? In programming classes, we learn how to use a CPU. In Engineering 270, we learn how to hook a CPU up to devices, motors, and lights and stuff. But in computer architecture, you actually learn about the design of it. How do you actually come up with, how do you make the decisions about what a CPU should look like? And a lot of that is about designing this data path. How are you going to move data around? And ultimately, it's just a bunch of multiplexers and a lot of clever engineering. All right, let's do a 5-minute break. And then I want to talk about compressed truth tables. And then I want to start looking at some data sheets and digging into some more sophisticated devices.